Good morning. Welcome to Physics Studio. What I'd like to do first today is to review right-hand rules number 1 and 2, and then we'll have a second video which will go over right-hand rule number 3, which is a little bit complicated. So let's begin. Okay, right-hand rule number 1. Refers to a current carrying wire. And we found yesterday, having done some experiments with the compass and the current carrying wire, that there's a magnetic field around a wire in concentric circles. And so if we have a wire carrying current in any direction, arbitrary direction, and we'll put the positive terminal here and the negative terminal here so that the current is flowing that way, we can find the direction of the magnetic field looping around the wire in concentric circles by pointing our thumb in the direction of the current, and then our fingers wrap in the direction of the field. So as we wrap our fingers around the wire, we find that when we hit the board above the wire here, we're going into the board. And so in that case, we're going to put X's here to show that the field is going into the board. And again, as we wrap our fingers around, imagining that our fingers go through the board, under the wire, and hit the board on the other side here, they're coming out. And so by our convention, if this is the crossed feathers of the arrow going in, we'll see the point of the arrow coming out here. And we'll call that B for magnetic field. And now we know that the strength of the magnetic field at some point A, right, a distance R from the wire, B equals mu 0, that's in Tesla meters per amp, times the current over 2 pi times the distance from the wire to the point. We can see that this is going to cancel out because mu 0 is 4 pi times 10 to the minus 7. So B equals 2 times 10 to the minus 7th I over R at any point R from the wire. Now, we can also represent this wire, right? We can represent it going in any direction on the surface of the board, but we can also represent the wire going in to and out of the board. So if we represented our current carrying wire like this, that would mean we're looking at a cross section of the wire and it's going into the board like that. And to apply the right-hand rule, we would put our thumb in the direction of the current and the field would wrap around in that manner. That would be B. So that's right-hand rule number 1. Pretty simple, right? Right-hand rule number 2 refers to the magnetic field that's formed inside loops or a solenoid. And it's pretty simple, but each of these loops is creating a magnetic field, and each consecutive loop, the fields are going in the same direction, so they add together. Now, in order to find the directionality of that magnetic field, we're going to follow the current, right? We follow the current into the loop, and it's circling around like that, and it comes out like that. We're going to wrap our fingers in the direction that the current is physically flowing, and our thumb points north. So in this case, the north of the magnetic field is here, and south is here. And we know how magnetic fields work, right? They point away from north and towards south. And so that's what the field is going to look like around that solenoid. Now, interesting thing, you might think, right, and it would not be unreasonable for you to think that maybe north always lines up with the negative and south with the positive. But if we had looped this solenoid in the opposite direction around the core, then we would find that north is this way, where the positive is. Similarly, we could switch negative and positive and run the current from here to here, in which case when we wrap our fingers around, we would find north is this way. So you can reverse the polarity of an electromagnet either by reversing the current or by reversing the direction of the wraps of the wire. Now, there's a little bit of a subtlety here when we talk about this. We have a magnetic field here, B, right? Looping, in this case, from north to south. And inside, it's fairly uniform, like that. If we have loops of wire, then the magnetic field is going to equal 2 pi times 10 to the minus 7th times the number of loops times the current divided by the radius of the loops. So that's for loops of wire. So the current's going like this. We know at any given point, like this point here, the current is going up. So by the right-hand rule, we see it's going in here, out here. And that'll be the same at every point that we take. The magnetic field at the center of that is going to depend on the radius. But for a solenoid, and I should say an ideal solenoid, and that means that the length of the solenoid is very large compared to the diameter. That factor drops out and we get what's a fairly uniform field in between. And in that case, the magnetic field is going to equal mu 0 times the number of turns per meter times the current, and it does not depend on the radius. So for just loops of wire, this formula gives us the magnetic field at the center of the loop. For an ideal solenoid, we can use this formula. And your book will tell you if they're talking about a solenoid. And we know that mu 0 equals 4 pi times 10 to the minus 7th n over L times current. So that's right-hand rules number 1 and 2. In the next installment, we'll talk about right-hand rule number 3, which tells us about the forces exerted on a current-carrying wire or a moving charged particle. So good luck with your skill sheet, and I'll talk to you in a bit.